two wires are made of the same material and have the same volume. However, wire 1 has cross-sectional area A and wire 2 has cross-sectional area 3A. If the length of wire 1 increases by delta x on applying force F, how much force is needed to stretch wire 2 by the same amount? So, we have this expression for Young's modulus, where Young's modulus is equal to stress by strain. And what are these words, stress and strain? The stress is the tensile force acting per unit cross-sectional area, and the strain is the extension divided by the total length. Therefore, Young's modulus is equal to the tensile force into the length divided by the cross-sectional area into the extension. The same is true for a compressive force F and a compression of delta x. So now we are given that the materials are the same and the volumes are the same. So what does that mean? We have y1 is equal to y2 and a1 L1 is equal to a2 L2, or L1 by L2 is equal to a2 by a1. So now let's take the equation y1 is equal to y2 and see what we can get out of it. This gives us F1 L1 by A1 delta x is equal to F2 L2 by A2 delta x. Why did I give no subscript to delta x? Because we are told that the wire 2 has to be stretched by the same amount. So both delta x's are equal and I can cancel them out over here. So this directly gives us F2 is equal to F1 into L1 by L2 into A2 by A1, or F1 is equal to F, L1 by L2 is equal to A2 by A1. So we have A2 by A1 whole squared. So this is F into A2 is 3A, A1 is A whole squared. So F2 is equal to 9F, and hence the amount of force needed to stretch wire 2 by the same amount is equal to 9F. This makes sense because if wire 2 has a larger cross-sectional area and a smaller length, then because of the bigger cross-sectional area, it is tougher to extend the wire. Also, because the wire is short, the same amount of absolute extension requires a larger amount of fractional extension, and hence the effect of changing the cross-sectional area while keeping the volume constant is squared.